Greetings and welcome back. So this is the final technical content of what I'm going to do in the course this year. And I have switched places where I'm staying, and the internet is so weak that I'm not able to actually link to my iPad. So I'm going to have to be reduced to doing my calculations by doing them ahead of time and then showing them to you in real time, which is not my favorite scheme. But anyway, the topic I wanted to discuss is phase separation. And the reason I wanted to talk about that in particular, I wasn't going to include it this year, but there's a beautiful paper that just came out from Christoph Weber and Frank Ulicker and Tony Hyman and the various people that did the work with them that was so cool and such a great example of physical biology that I just couldn't pass up the opportunity to talk about it. So what I want to do is I want to describe to you what I recently heard described as the most important step forward in cell biology in the last 15 or so years, and that's the general subject of membraneless organelles. So, there is an element to this that I would call a bit of a fad. And, I've been keeping track of fads in physics and in biology for the last 30 years. And it's fascinating, to see how things acquire a life of their own. But it's a really fun arena. And, there's many things that can be said about it. But what I'm gonna do today is basically try to focus on some of the key concepts, and then we'll do a little bit of the math that goes with it. So first thing I wanted to do was take you back to roughly 2009, if I remember correctly. Tony Hyman was serving as a faculty member in the physiology course at the Marine Biological Laboratory, and Cliff Brangwyn was working with Tony, and they were looking at C. elegans, as you see here, and in particular, they made some observations about, I think they're referred to as P granules. And the observation really was that these P granules appeared to behave like liquid droplets. And the outcome of this, I'm not going to go into the details. I just suggest you go look at the science paper that came out to get an opinion or sort of a sense of what was going on. The thing I wanted to point out is that this kicked off a flurry of activity that has involved all sorts of really excellent scientists trying to come at this from all sorts of different angles. And it's been found now that this is quite ubiquitous. And the reason that I think it's important to consider is that the first time we learn about organelles is probably in a high school biology class where we learn about the beautiful nucleus and the ER and the Golgi and mitochondria and so on. And that's fantastic. And we learn things, for example, about the fact that these are membrane-bound organelles. Well, the nucleolus, just for example, which we talked about at the very beginning of the term, and the P granules and a variety of other examples are membraneless, and yet they're still organized. So what's shown here is the early embryo of C. elegans. And all that I really want to call your attention to is the existence of these apparent droplets, okay, what are shown in green on the left, and they're actually partitioned between the two sides of the cell. And on the right-hand image, what you see is that these things are somehow an assembly of proteins and RNAs, and I'll maybe come back to that a little bit, but not much. So one of the really interesting things that has been considered is why would we say that these things look like droplets? And the experiments that were put forth to try to examine the dynamics of these phase-separated putative droplets included, as you see in the film strip at the top, seeing that they flowed. So that was one example, and I'm not going to go into the details of that. You can see that in Brangwyn's papers. The next one, the middle image, shows you that they merge and coalesce, another feature that we're used to from droplets. And then in the bottom, what was shown is that they're dynamic using fluorescence recovery after photobleaching. And I just remind you, for those of you that have been taking the course, that you had the opportunity to actually calculate fluorescence recovery after photobleaching. We did, that was one of the places we did Fourier series earlier in the term. And so, all of these are the hallmarks of a certain kind of dynamism that we would normally associate with liquids rather than solids or gels or that kind of thing. So, so I just wanted to point out, that this field of phase separation is not new even to biology. And here I'm showing you some of the beautiful work done by people like Sarah Keller at the University of Washington. I'm a particular fan of the things that she does. And here, what you see is a phase diagram. This is a ternary phase diagram. When I say ternary, that means there's 3 molecular constituents. So 2 lipids, which you see in the bottom, and then cholesterol. And these things phase separate into these beautiful domains that you see on a giant unilamellar vesicle. So my point here was just to say that we already knew in the context of membranes that that lipids and cholesterol, that they would phase separate, and there was much that was already done about the behavior of these things. This is work from Amy Gladfelter's lab, if I remember correctly. And I'm just going to read you at least the one on the left. I'm going to just read you the caption that we wrote about this. So it says, multiple distinct types of membraneless intracellular condensates can form both in the cytoplasm and in the nucleus. A, 2 different kinds of RNA-containing condensates form in filamentous hyphae of the fungus Ashbia gaspi. In these images, nuclei are labeled in blue. 2 different messenger RNAs, BNI1 green and CLN3 pink, associate with the condensates in the cytoplasm. So, very, very cool, very interesting. And then on the right is an image of a HeLa cell nucleus showing 3 distinct types of membraneless condensates of different sizes forming in the nucleoplasm. And, you can see the nucleoli and the PLM bodies and so on. So, I'm just trying to point out, this is really to whet your appetite. You can look up these 2 papers, and, Amy Gladfelter does really interesting stuff. I'm hoping and imagining that there's probably a video of her online talking about some of the beautiful things that she's done. So what I want to do is I want to primarily be in theorist mode, and here I'm gonna riff on what a phase diagram actually means. So what I want you to imagine, the way I'm going to think about this, is that we have 2 different categories of molecules, and I'm going to call them red and blue. Like I'm not going to specify what they are. And what we're going to do is, at a given temperature, we're going to pipette in different fractions of red, and then we're going to look at the resulting phase behavior. And so what you see is that in 1, of course, it's pure blue, and in 7, it's pure red. So phi, which is the fraction red shown on the x-axis, runs between 0 and 1. And, that's fine. So point 2 is very special. So point 2 is the terminus of the region in which you have perfect mixing. So what I'm saying is that if you look at number 2, it's got a little bit of a purplish tint to it. And the reason for that is that there are some red molecules in there, but they're mixed around. And you can think about this, for example, in the context of lipids, where there's something known as the critical micelle concentration. And if you're below that concentration, then the lipids will be wandering around by themselves. So once we pass 2, what we're doing now is we're tuning the fraction of red. And once we pass point 2 at that temperature, we now enter the phase separated regime. And what that means is that the material will separate into 2 different pieces, one of which is at the concentration at 2, and the other of which is at the concentration at 6. So the 6 phase is red rich, the 2 phase is blue rich, but neither of them are perfectly blue or perfectly red. They're a mixture. And so what's happening is that the relative amount of the blue rich and the red rich phases is changing as we tune along the x-axis by pipetting in different amounts of red. So this phase diagram is an equilibrium statement. If we let the system sit there and attain its equilibrium state, it's telling us about the terminal privileged state, which, if I'm to the left of point 2 or to the right of point 6 at the temperature shown here, then I will be in the mixed state. If I'm in between the concentration 2 and 6, then I will be phase separated. What you see as you increase the temperature is that the region over which we have phase separation is narrowed. And that kind of makes sense because what I want you to imagine is that if we raise the temperature enough, the entropy effect is going to carry the day. In other words, at some point the molecules are going to say, well, the entropy is so important to maintain that we're not going to get the advantage of being near our red friends, for example, if you're in the red-rich phase. So that's what I mean by a phase diagram. And here I'm trying to give you an impression of the kind of thing that happens. So this is just recapping the previous diagram. And that is, on the left-hand side, what I'm showing you is what we pipette. In other words, let's say that I violently mix up some reds and blues at a given concentration, which I'm going to call phi pipetted. What do I mean by phi pipetted? That's a point on the x-axis here at which I've decided what fraction of the molecules are red. And then I wait. And what will happen is that it will phase separate into the two regimes, which I'm going to identify as phi prime and phi double prime. I previously called those 2 and 6 here. So 2 is phi prime and 6 is phi double prime. And actually, I said it backwards. Phi prime is actually the red-rich one, so that's 6, and phi double prime is 2. And then the relative amount of phi prime and phi double prime is characterized by this quantity f. That's this fraction. And this comes from what I will refer to later as the lever rule. Basically, all it is an imposition of conservation of mass. If you count the number of red molecules, you should check me and I hopefully didn't make a mistake. But if you count the number of red molecules on the left and you count the number of red molecules on the right, what you'll see is that they're the same. But the blue-rich phase has very few red molecules and the red-rich phase has very many. And so what we do is we balance the amount of phi prime and phi double prime such that the total number of reds and the total number of blues is equal to what we have pipetted. So that's what's going on in this picture. So what we're going to do, I'm gonna foreshadow, and then I will go over to the other notes. What we're going to do is I want to now compute a free energy. So let me say what I mean by that. So we're going to, when I say I want a free energy, what I mean is that I want to write a quantity, free energy of phi, where phi is the fraction red, and that's going to be U of phi minus T times S of phi, where U of phi is the energy piece and S of phi is the entropy piece. And what I'm showing you in this diagram is what's known as mean field theory. It doesn't matter what it's called. It's kind of what I think you might do yourself, which is instead of calculating all the red-red interactions, all the blue-blue interactions, and all the red-blue interactions, what we do instead is we say, well, I'm going to imagine an effective interaction where the fraction of the interactions that are red-red is given by phi squared, because the probability of finding two reds next to each other is phi. That's the probability of finding a red, times phi, which is the probability of finding another red on the next lattice site. And so it's basically a weighted average over the red-red, the blue-blue, and the red-blue interactions. That's what we're indicating by this energy. And then the second thing we're going to do is we're going to compute the entropy. We've already done this. So if I have a total of n tote sites, which is the same as nr plus nb, so the nr is the number of red molecules, nb is the number of blue molecules, the total number of molecules, and hence the total number of lattice sites is nr plus nb. If I want to find the entropy, I use the Boltzmann definition. S is equal to kb log w, and the total number of ways of rearranging the reds and the blues is given by exactly the expression that I show you there, which is an expression that we've used a bunch of times this term. So we will work that out as well. And the thing I want you to see is that the energy as a function of phi adopts this form, the entropy as a function of phi adopts this form, and when we assemble these pieces, we actually will get a total free energy, which is given in green. So remember, the entropy is Ts, but free energy requires us to subtract. So we have U minus Ts, or E minus Ts in my language here. And so we put those two pieces together and we find a free energy as a function of the fraction that's red. And then all we're really trying to do at that point is we're trying to find the free energy minimizer. Okay, that's the objective of the calculation. And we're going to use what's called Flory-Huggins theory in order to carry out that calculation. So let me just see what else I have. So this is the part having to do with the lever rule, which I'll come back to, I think, in the next discussion. And this is the outcome, basically, of the phase diagram, which is what we're trying to do is we're trying to find the free energy minimizing choice of phi prime and phi double prime. And one way of representing that is shown here. So we're doing a minimization of a free energy at different temperatures, and we're trying to find what choice of phi double prime and phi prime will minimize the overall free energy. So you basically can compute the free energy, the phase diagram. So the reason, again, that I wanted to do this vignette is that after we do this Flory-Huggins theory, I'm going to come back and talk about this quite amazing paper in which they put this whole set of ideas to the test. They do this by doing temperature cycles on C. elegans, and they see the reentrant phase separation into these P granules, and then they're dissolved. That's what's shown here. I'm going to talk about it later, but in some sense, the graph at the top just blows my mind, because what it's showing you is the volume of P granules is a function of temperature, and they're basically doing a cycle in temperature, and as a result, they're doing a cycling of reversible formation of these condensates. So that's what I wanted to say by way of introduction. So in the next vignette, what we'll do is we will talk about the Flory-Huggins theory